Hello everyone, my name is Abdellah Aznag. I'm a first-year PhD student in the IOR department at Columbia University. And today I will be presenting my work, MNL-Bandit with Knapsacks. This is a joint work with Professor Vineet Goyal and Noémie Périvier. Before I start my talk, I would like to thank my co-authors, Vineet and Noémie, my department, as well as the committee of EC'21. To understand the motivation behind our problem, let us look into the basic retail framework. You have a seller who has a large set of products and he interacts with customers during a time horizon T. Since the customers, they tend to behave in a certain way, for simplicity, let's just assume that this behavior is the same. This is not a very costly hypothesis, as we can always cluster the behaviors and focus into each type of behavior at once. So what happens when at a given time T is a customer arrives and he is confronted to a large set of products, and in our configuration we allow the seller, we give him the possibility to select which subset of products to show. So the customer, he does not see all the items, but only a fraction of the items which the seller controls. Then based on this subset of items, the customer, he makes a decision, either purchasing one of the offered products or leaving without making any purchases. We model this framework in the well-known, well-studied MNL model, where you have n products and each product has a parameter vi, which interpretation is, it models how attractive the product is compared to the other products, so that when the seller offers subset ST, the customer, he makes the purchasing or no purchasing decision based on probability of buying item I, if I is offered, is VI over 1 plus the sum of offered items, of the parameters of the offered items. Notice that when you sum these probabilities, the sum is not 1. It is normal because we keep the remaining probability for the no purchase option. The expected revenue when making decisions S1, S2 until ST is the sum of R multiplied by these probabilities for the offered STs. And the goal of the seller is to maximize his revenue over the time horizon. The problem we are studying is how to optimize this revenue under two additional constraints. The first constraint is each product has an initial inventory Q, and once this inventory is consumed, it cannot be replenished. So once depleted, you cannot refill it. And the second constraint for the seller is that he does not know the parameters VI. There are some non-trivial difficulties to this problem. Probably the most important one is that even in the offline case, even if the seller knew the parameters, the optimal algorithm is not known. So the offline case is hard. The second difficulty is that the seller does not know the VIs, and so there is a learning constraint. So the seller has to somehow learn these parameters, and he only gets to observe the purchasing decisions. And the number of possibilities to offer at each time is exponential in the number of items. So since no optimal algorithm is known for the offline case, the benchmark is not trivial. So we consider the following benchmark, which is the solution to a simple LP problem. We claim that this LP gives an upper bound on the optimal revenue in the offline case, and in the online case as well. Why is that? It's easy to see that. Just notice that any feasible policy is also feasible in the LP. As the interpretation of this LP is, we just transform the hard constraint into a constraint that must be satisfied in expectation, while allowing assortments to be fractional. So our goal and the seller's goal is to find a policy that minimizes the following regret, which is guaranteed to be an upper bound on the classic regret, which would be the offline minus the online revenue. So this is our benchmark, which is t multiplied by opt, with opt the solution to this LP, minus the expected reward generated by any given policy that offers S1, S2 until S of big T. Our main result is that we have constructed a policy that satisfies the following regret. This regret can be deconstructed into three relevant terms. We're going to start with the square root of t here. The dependence on t is near optimal. The second relevant term is this 1 plus this quantity, which depends on the parameter v's and the parameter qmin. It is quite natural because it basically says that your statistical complexity when qmin is small is going to be very large. So you will not have enough trials so that you achieve a nice online policy. In order to understand this k square root of k multiplied by square root of n, just notice that n can be very large, and using all of the n's using all the n's at the same time, and optimizing over programs which use n at the same time can generate a high regret. So what we do is we add this additional constraint that we constrain our assortments so that their size does not exceed k. This makes the targeted value just a bit smaller, and it makes the complexity, the computational complexity a bit higher, but it can make us gain a lot in terms of statistical regret, because this k here can be much smaller than this n. And so the total statistical complexity can be small. So this k here is it trades off computational efficiency for a lot of statistical efficiency. Our policy works because of mainly two key properties. The first property is how it chooses the items. It chooses very attractive items so that the revenue is high enough, but it also chooses the items so that they are relevant and none of the products is depleted. So the consumption rates are steady, and the consumption rates are evenly balanced with high probability. Before I dive into the specifics of the policy, I'm going to cite some very notable work which served as the conceptual building blocks of our policy. There has been a lot of work regarding dynamic assortment optimization, but unfortunately, finite inventory constraints were not yet addressed. And there also have been a lot of work on bandits with knapsacks, where you have a set of arms and you receive a reward, but you also pay a cost and you have a finite budget. So how do you do? So there has been work in that. And we were deeply inspired by this work, as in our policy, we view each assortment as an arm in bandits with knapsacks. This does not trivially solve the problem, as this way of viewing things has the disadvantage of having exponentially many arms. And so we can't trivially solve the problem using these results. There's also a paper by Chung and Simchi Levy, which studied this problem and studied the dynamic assortment optimization problem under the inventory constraints. And he offered two algorithms, one of which does not achieve near optimal regret, and one that achieves near optimal regret, but is not computationally efficient. Before presenting the algorithm, we're going to answer the two main questions. How do we explore? So how do we estimate the models of the parameters? And given the estimates, how do we exploit that partial information so that we know which assortment to offer at time t? To estimate the parameters, we use the same, we use an already used estimates, which is very natural. It's called the epoch system. And it gives us a confidence bounds, a very good confidence bounds on VIs. So the key idea behind these estimates is that we can view VI as an attractivity ratio. It basically measures the ratio that the frequency that a number of item I is bought versus a no purchase item, versus a no purchase. So the exact estimator is that we basically just offer a fixed assortment a consecutive number of times until no purchase happens. So we call this an epoch. And then we estimate, at the end of the epoch, we estimate VI as the frequency of appearances of I during this epoch. And we prove that these estimates are good estimates of the V's. For the decision-making process, actually, we do not offer a deterministic assortment, but we actually randomize over a probability that is the solution to a certain LP. So how do we choose that distribution? We basically overestimate the revenues and we underestimate the cost of each item. And we choose a distribution that is the solution to a given LP. This LP, we just want to maximize the overestimation of the revenue under the underestimation of the inventory constraints. And we offer a sampling of this distribution. Notice that we do not have the same inventory constraint, but we add this shrinkage factor omega. The interpretation of this factor is that we just transform this feasibility on expectation to a feasibility with high probability, since we're interested in hard constraints. And this is how this omega is chosen. In order to see why the hard constraints are respected, just view the consumption of each item I. This consumption is exactly this quantity, which is equal to this quantity on expectation with respect to the offered assortment at each period. Since we have at our disposal an underestimation of this probability, we replace it by this underestimation. And remember that we play ST as a sampling of a given distribution, YST. So just we replace this value with its expected value under this sampling, which gives this quantity. And remember that this last expression is exactly this expression right here, so that this distribution satisfies the following inventory constraint. And notice that we have generated minor errors here and here and here. And so we choose omega. This is where the choice of omega comes up. We choose omega so that it covers for these mistakes with high probability. This is how we prove that these hard constraints are respected with high probability. So regarding the high revenue, the proof is conceptually the same, only this time, instead of underestimating the probability, we overestimate it. And we prove that the cost of this overestimation is actually small, as the losses of these 4 steps are small. And also in our choice of omega, we choose omega so that this quantity is not that large. And this is how we prove that the revenue is high enough. And I would say we are done. But the problem that we solve at each step, and most importantly, the sampling of YSL is not it's not trivially tractable. Actually, it has an exponentially many variables, so we have a tractability problem, which we need to overcome. So how do we do that? First of all, we don't look at the problem, we don't look at the primal, we look at its dual. And we all know that this dual can be solved efficiently if we build a separation oracle. The only thing is we don't know how to do that. So how do we overcome this? We actually don't look at the dual, but we look at a tweaked dual by introducing new capacities and new revenues. This gives the following problem. And we look at these constraints, these new tweaked constraints. They can algebraically be interpreted as a difference of two MNLs. So instead of looking for a separation oracle for the original dual, we just have to build a separation oracle for this new dual, or equivalently solve this problem, which is the difference of two MNLs. And once more, we don't know how to do that. There is no known efficient separation oracle, but we can use known techniques related to the MNL literature that solve this dual. We know how to build a weak approximation guarantee that solves the problem. That gives us a lower bound on the revenue generated by S by solving this problem. And actually we find through computations that the error bound is actually small enough to approximately solve PL. And this gives a computationally efficient policy. So that way we're done. We have built a computationally tractable policy that provides a good regret bound, which is actually near optimal in the large inventory setting. However, there's still work to be done here, as we can there are some natural questions that we can ask ourselves. The first one is, how can we extend this algorithm? The choice model we used is very fundamental, and but it can be extended to more general choice models. And one question is, can we extend this algorithm to these choice models? And if not, how can we solve that? Second question is, can we improve the efficiency of our policy? Because even though it is a tractable policy, it can be regarded as very costly as it uses the ellipsoid algorithm and separation oracles. So can we build more efficient algorithms that solves the same problem while guaranteeing the same or even better regret bound? I thank you for your attention, and if you have any questions, please feel free to contact me.